So in the previous lecture, we talked about all the steps that are required to preprocess your text in order to convert your documents into lists of integers so that they can be ingested by a neural network. So now the big question, how do you do this in PyTorch? Well, it's not done in PyTorch per se, but it's part of the PyTorch ecosystem. Just like how specialized computer vision operations are done by the Torch Vision library, specialized NLP operations are done by the Torch Text library. This is also automatically installed in Google Colab, so there isn't anything special you need to install on your own if you use Google Colab. Unfortunately, the syntax is quite strange, so bear with me as I try to make it digestible. First, we're going to assume that our task is text classification, which it is, and it's going to be a many-to-one task. That means for each document, which is a sequence of words, our prediction is going to be a single label for that entire document. That might sound a little bit abstract, so to give you a concrete example, think of spam detection. Your input is an email, which is a sequence of words, and you would like to output a single label, spam or not spam. For Torch Text, we'll want this data to be formatted as a CSV, with one column for the label and one column for the input text. I assume that at this stage you know how to write a program in Python so that if your data does not come in this format, you know what to do to convert it into the required format. The next step is to create field objects. Field objects are part of the torchtext.data module. Both the inputs column and the targets column will be field objects, but with different arguments. For the input data, I want to pass in the arguments sequential equals true, batch first equals true, lower equals true, and pad first equals true. Let's run through these quickly, although they should be pretty intuitive already. We set sequential equal to true since the data is sequential. Each value is a sequence of words. We set batch first equal to true because we want the n dimension to come first and the t dimension to come last. We set lower equal to true because we want to lowercase the words. This isn't always necessary, but our data set is pretty small, in which case it's usually a pretty good idea. And lastly, we set pad first equal to true so that we use pre-padding instead of post-padding. We already discussed why that might be desirable, although you should try both just to be sure. For the label, we're going to create another field objects, but with an entirely different set of arguments. Specifically, we're going to set sequential equal to false, use vocab equal to false, and is target equal to true. Since the target is not sequential, we set sequential equal to false. This should be clear. We set use vocab equal to false, which might seem strange, but let's think about it. Remember that there are a whole bunch of text preprocessing steps that we need to do, one of which involves assigning a unique integer to each word in the dataset. This is the process of building the vocabulary of words in the dataset. Of course, such a process wouldn't make sense to do on the targets because the targets are just numerical labels. So we set use vocab equal to false. Finally, we set is target equal to true since this field is for the target column after all. In my opinion, this could have a better API, but it is what it is. You might also want to consider how these arguments might change if you were doing something like neural machine translation. The next step is to instantiate a tabular dataset object, which is also part of the torchtext.data module. So now you understand why we want to create a CSV to store our data. It's because a CSV is a table, and Torch Text only knows how to read tabular datasets. Now you might think, it might seem kind of limited to only have tabular datasets. What if we need a dataset that is not tabular? But if you think about it, pretty much every text dataset you can think of will probably fit into this framework, whether that's sentiment analysis, spam detection, parts of speech tagging, machine translation, and so forth. Even if it's unsupervised learning and all you have is just one document per line, that's still technically a CSV. So all these different kinds of datasets can fit into a CSV format. And as long as you're a competent programmer and you know how to make your own CSV, this should not be an issue. So let's go through the arguments one by one so you know what they mean. The first argument, which is the path, should be clear. It's the path to the data file where your CSV dataset is stored. The second argument is the format, which I've specified as CSV. Other options are TSV and JSON, but these are not so significant in my opinion. A TSV is just like a CSV, but with tabs instead of commas. It's trivial to switch between them, so there's no advantage to using one over the other. JSON is nice, but it just adds extra characters to your data file without any real benefit. You can use it if you want, but again, there's no distinct advantage, unless for some reason your data already came in that format. Next, we set skip header equal to true, since in our dataset, there is a header row that we'll want to ignore. Finally, we set the fields argument, which is a list of tuples. Each tuple contains two items, the name of the field and the corresponding field object. I'll call the first one data and the second one label. The next step is to split the data into train and test sets, which is nice and easy with TorchText. Just call dataset.split, and this returns two items, your train set and your test set. As input, you can pass in an argument called split ratio to say what percentage of the dataset you want to be part of the train set. By default, this is 70%, so I haven't bothered to change it. The next step is to call the build vocab function on our text field from earlier. This assigns a unique integer to each unique token in the dataset. So you can imagine that internally, TorchText is doing the tokenization and all the other text preprocessing steps that we discussed earlier. This function by itself doesn't return anything, but after doing this, we can access the vocab attribute in the text field, which returns a vocab object. So what is a vocab object? Well, the vocab object contains that word-to-index mapping that we talked about in the previous lecture. You can access it by calling vocab.s2i. So s2i should remind you of C-style naming if you've ever coded in the C programming language before. This returns a dictionary where the key is a token and the value is a unique integer that corresponds to the token. Additionally, you can call the vocab.i2s function, which returns the opposite. In particular, it returns a list of all the unique tokens in the dataset. Now you might be wondering, how can the opposite of a dictionary be a list? Well, remember that a dictionary is nothing but a set of indices and corresponding values. So too is a list. A list has the indices 0 up to k-1 if the list has length k. The values of a list are just the elements of that list. So if I call vocab.s2i of dog and I get back 211, then if I call vocab.i2s of 211, I will get back the string dog. So they are inverse mappings relative to each other. Now you might be wondering, who cares and why do we even need these mappings? Well, if all we want to do is text classification, then we don't necessarily. But there may be instances where, let's say, you're doing text generation or machine translation, where the output of the neural network is a sequence of integers. Of course, in order to turn that into text, you have to convert that sequence of integers back into a sentence. And in order to do that, you must know which integer corresponds to which word in your vocabulary. Okay, so at this point, we have a trained dataset and a test dataset. Now what? Well, imagine your dataset is huge. So huge that, just like our image datasets, we would rather do batch gradient descent rather than full gradient descent. So just like in Torch Vision, where we had an iterator over our image dataset, we would like to use an iterator from TorchText for our text dataset. Here's an example of how we would create an iterator for our text datasets. The first argument is a tuple containing the datasets that we previously created. The second argument is a sort key. The idea behind this is that, because we'll need to pad each batch of our dataset, we would like each of the sentences in each batch to be of similar size. So by specifying the sort key to be a function that returns the length of the text field, we can tell torch_text to organize the batches so that each sentence will be of roughly the same length. Next, we pass in batch sizes. This is a tuple containing the same number of elements as we have datasets. Basically, the first number represents the batch size of the trained dataset, and the second number represents the batch size of the test dataset. Usually, we can specify the batch size of the test dataset to be larger, since it doesn't need to do any heavy processing other than just making predictions. Finally, we set the device argument to the device object that we've been creating in all of our notebooks, which refers to the GPU. So this means that our dataset will be automatically placed on the GPU without us having to do so manually. Alright, so at this point, you should be asking, what's next? Since we now have iterators that can loop through our train set and our test set and return batches that are just n by t arrays of integers corresponding to each sentence, there's nothing more to do. We can pass this data directly into our RNN for both training and testing. So you can imagine that our training loop will look like it usually does, as will our loop to calculate the accuracy. One minor caveat is that the torch_text iterator gives us back a target that is only one-dimensional. We know that in PyTorch we like to have two-dimensional targets. So we can call the view function to convert each batch of targets from an n-length one-dimensional array to an n by 1 two-dimensional array.